Hello guys, welcome to a brand new video. I would really want to thank you all guys for subscribing and then sharing this channel, and then I would continue to do my best to make videos that will help you all. Now we are straight away looking into this question, a question on probability density function. So this is actually a question. It says the probability density function of a time to failure of an electronic component in a copier that is given in hours is given by, this is the function, the probability density function. And it says we have to calculate the probability that a component lasts for more than 3,000 hours before failure. Secondly, we have to calculate a component fails in the interval 1,000 to 2,000. And then C, we have to calculate a component fails before 1,000 hours. Now, it is important to know how a function, this is actually an exponential function, right? So at least if you have a mental picture of how that kind of function looks like, it helps you in solving, right? It really helps in solving. So this function we have over here in the question, this is how it looks like over here, right? An exponential function. The first part of the question said we are to calculate what? The probability that the component lasts for more than 3,000 hours. So if this is our function and we want more than 3,000 hours, this is from what? 0. And it goes on and on and on. Remember, for exponential, as your number, as the value of x approaches infinity, then your function is also approaching 0. That is why this one is trying to end over here, you see. Now we want the probability that the failure exceeds 3,000. This is our 3,000 here. So it will be all of this. We'll be calculating this area. In a bit, we'll be doing that. Then the second part of the question was we were to calculate the probability that a component fails in an interval 1,000 to 2,000. So if we come back here on our diagram, this here is where we have our 1,000. And this here is where we have our 2,000. So we would be using integrals to give us the area of all of this over here, right? And then our last part was calculate the probability that the component fails before 1,000. It fails before 1,000. So if we come back to our diagram, before 1,000. So before 1,000 will be from 0 all the way towards 1,000. And it is what I have represented here with what? The red. So let's quickly go into the first question. Now we have to take note that our probability density function was given as, that is f of x. F of x equals 1 over 1,000, then e to the power negative x over 1,000, right? For x greater than 0. So if from this we want to get our cumulative distributive function, then our cumulative distributive function is equal to the integral of the probability distributive function. Easy. So that is from 0 to your x as your limit, right? So you have to take note that our f of t is equal to what we have over here. So 1 over 1,000 e to the power negative x over what? This 1,000 over here, right? So now substituting it into this one to give us our probability, substituting it into this one to give us our cumulative distributive function. Then it means we are going to have f, easy. And if we have to integrate this one, this is a constant, so it still remains as it is. Then we have times integral of exponential. We are going to differentiate this and then use it to do what? Divide. So integral of this exponential, we are going to differentiate this and then it comes to multiply. And that alone should give us a negative 1,000 is then times all of this that we have over here. All right. which is e all to the power negative x all over 10,000 to multiply. It simply means this here cancels out this. You see, to have negative e to the power negative x all over what? 1,000, with our limits being what? 0 to x. Do you see? So we can copy this and then find the exact value by substituting the values of x and then what have you into it. So substituting our limits, we have negative e to the power. First of all, we have a minus, so it's from x to 0, right? So you have a minus x, which is the upper limit, over what? 1,000 minus that of 0. So e to the power negative, you can say negative 0 over the 1,000. Now, this 0 over 1,000 here still gives us 0. So simplifying further, we have negative e to the power negative x all over 1,000 minus e to the power 0. And we know any number to the power 0 gives us 1. Alright? So it simply means we are going to get the value. But before that, let's take note of one thing here. This negative here is affecting this whole thing. Do you see? So if this negative is affecting this whole thing, so you don't overlook it, right? The negative we had here affected the whole thing in the bracket, right? Then you have your what do you call it? Negative into bracket. So as we have it now, we are then going to have. So as we have it now, because this negative affects the whole bracket, we are going to get negative e raised to the power x over 100, right? Then plus 1. So rewriting our function now, f of x is equal to, we can write the 1 first, 1, then minus e to the power negative x all over 100, right? So now this here is the what? CDF of the exponential distribution, right? This here. So to write it in and then make it more presentable so that it satisfies the range of values we were given, we are going to say our cumulative distributive function f of x now is going to be equal to the probability of our random variable x being less than or equal to x, right, which is equal to, so we have these functions, 1 minus e to the power x over 1,000, all right, for x greater than what or equal to 0, and then 0 for x which is less than 0. We got this range of values from the question, right? And then we are saying 0 for anything that is less than the 0, right? So with this now we can solve our questions. Let's go into that. So rewriting all that, this is our function we have over here. Then back to the first question. So it says the probability, we have to calculate the probability that a component lasts for more than what? 3,000. A component lasts more than what? 3,000. So now that we have been able to get our cumulative distribution function, let's come back to the question. It says we have to calculate the probability that a component lasts for more than here means greater, right? Greater than 3,000 hours, right? Greater than 3,000 hours. So let's come back here, and then we said for our cumulative distribution, we said for our random variable x less than small x, this is what we should write over here. But then what we want to solve for is more than. So more than would then be what? That our random variable x is more than 3,000 will then be equal to what? The exponential variable, our exponential value, exp of negative 3,000 over what? 1,000. Easy. We are not going to use the 1 minus. Do you know why we are not going to use the 1 minus? Let's come back to what we have over here. Now they said the probability that x is greater than. So most of the times we subtract the 1 because it gives us directly what is here. And we know all of this is 1. You see? So if you want the remaining, that is where we subtract what we have gotten here from 1 to give us the remaining. But this time around, it is this is what we want and not the remaining from 0. See, that is why we are not subtracting the 1. I hope that makes sense. Yes. So solving this one further, we are going to get what? Our exponential of what? Negative 3. You see, so we all know these 3 zeros will cancel out to these 3 zeros. Hence, simplifying, you can punch this on your calculator and you are going to get an approximate value of 0.09. You can punch this on your calculator and you are going to get an approximate value of 0.0498. And that becomes the probability that the components last for more than 3,000 hours. Now let's look at the next question. The next question says you have to calculate the probability that the component fails in the interval from 1,000 to 2,000. 1,000 to 2,000. So in this case now we have a lower and then an upper limit. Remember that we have a lower and then an upper limit. So in our diagram here, the one in green is what we are actually looking for. The portion I have painted green is what we want. The probability that the component will fail within this interval. So how are we going to go about that too? So first of all, what do we need? We are going to solve for the probability that a random variable x is between 1,000 and then what? 2,000. And that is just the cumulative of 2,000 minus the cumulative of what? 1,000. Easy. So now solving for the cumulative of 2,000, we know f of 2,000 is then going to give us 1 minus initial value of 2,000 over 1,000, right? And cancelling out whatever you have, you are going to get 1 minus the exponential of negative 2. Easy. So that is equal to 1 minus e to the power negative 2. Then we will do the same for the second one. So cumulative a negative 1, because all this here gives us 1. So this simply means that the probability we are looking for of a random variable being between 1,000 and then 2,000 is going to be equal to that of 2,000 minus that of the 1,000, which gives us 1 minus e to the power negative 2 minus that of the 1,000, which was 1 minus e to the power 1. Simplifying further, we have 1 minus e to the power negative 2 minus 1. Then this and this gives us plus e to the power negative 1. We have 1 minus 1 giving us what? 0. Easy. Then now we are going to have e raised to the power negative 2. Not forgetting our negative in front of it. Plus e to the power negative 1. You see? Now at this point, you can punch it on your calculator. All this on your calculator. And that is going to give you and that is going to give you a 0.2326. So that becomes the probability that that the component fails in this interval, or in other words, that is the area of the green portion we have over here. Now let's look at our very last question. It says we have to calculate the probability that the component fail before 1,000 hours. You have to calculate that it will fail before that. So before that now represents all this red region over here. Before, it represents all this red region over here. So how do we go about that as well? So for it to fail before 1,000, then we are looking for the probability that our random variable x is less than what? 1,000. You see, which is equal to our cumulative function, which is equal to our cumulative distribution function at f equals at f of 1,000. You see, then now we do our substitution. We know f at 1,000 is going to be equal to 1 minus the exponential at what? Negative 1,000 over 1,000. Alright, and this is simply 1 minus the exponential at what? Negative 1. Alright, that is e raised to the power negative 1. So simplifying, we have 1 minus, if you punch this on the calculator, you get 0.3679, or if you are using tables, you can also get that from that. And then evaluating this further, we have all these 1 minus all these, giving us a value of 0.66321. So this simply means the probability that our random variable x is less than 1,000 is given by what? 1 minus is equal to 0.6321. So this is basically it for this particular question. And then it's very, very good you understand the graphical representation of it. At least if you understand how it looks like, it helps you know what formula to use when. Alright. So thank you very much for coming to the very end of this video, and kindly like and subscribe and let me know the mathematical problems you want me to address for you. Peace.